July 23, 2015, NASA, using the Kepler Space Telescope, announced a groundbreaking discovery, the exoplanet Kepler-452b, located about 1,400 light-years from Earth. A world considered one of the most promising candidates for life beyond our solar system. What makes Kepler-452b remarkable is its orbital period, 385 days, just 20 days longer than Earth's year. It receives about 10% more stellar energy from its Sun-like star. This creates an average surface temperature estimated at around 80 degrees Fahrenheit. Ideal conditions for maintaining liquid water, the essential ingredient for life as we know it. But what truly captures our imagination is its parent star's age, about 6 billion years old, making it 1.5 billion years older than our Sun. This suggests that Kepler-4b has had ample time to develop complex conditions that could nurture life. These factors raise an astonishing question. If life once emerged there, what would it look like today? Would it resemble humanity, or something far beyond our imagination? As we set out to explore Kepler-452b, we are not only uncovering the planet's extraordinary scientific features, but also chasing clues about life's possibilities, pushing us to reflect on where we stand in this vast, mysterious cosmos. For decades, scientists have tirelessly developed methods to reveal the astonishing diversity and hidden potential of the cosmos. Among the most groundbreaking techniques are two approaches that have transformed our understanding of distant worlds. The first is the radial velocity method, based on a fundamental principle of physics. When a planet orbits a star, their mutual gravitational pull causes the star to wobble ever so slightly. This motion creates a Doppler effect, a tiny shift in the star's light spectrum. By measuring these subtle variations, astronomers can infer the presence of an orbiting planet and even estimate its mass. Though indirect, this technique has unveiled hundreds of exoplanets, particularly massive ones close to their stars. The second is the transit method, which detects the faint dimming of a star's light as a planet crosses its face. From the degree of dimming, scientists can determine the planet's size relative to its star. By tracking how often these events occur, they can calculate the planet's orbital period. This method has proven invaluable for identifying worlds similar in size to Earth or even smaller. To gauge how Earth-like a planet truly is, researchers use the Earth Similarity Index, which factors in key characteristics such as radius, mass, surface temperature, orbital position, and even estimated gravity. By these measures, Kepler-452b stands apart from most known exoplanets, igniting hopes of finding a world that mirrors Earth's potential. This discovery sparked hopes of finding a world with conditions similar to Earth. With an ESI of 0.83, a radius about 1.6 times that of Earth, and an orbit squarely within its star's habitable zone, Kepler-452b emerges as an extraordinary candidate. But there is a sobering truth. Being in the habitable zone does not guarantee habitability. Countless factors can extinguish life's chances. A planet might lack an atmosphere, or possess one too thin, too thick, or devoid of protective magnetic fields. Tectonic activity, or the absence of it, can shape a planet's destiny. These are all critical factors for sustaining biological evolution. And tidal locking can condemn a world to extremes, one hemisphere scorched in eternal daylight, the other frozen in perpetual night. A haunting example is Proxima Centauri b, a planet within its star's habitable zone, yet trapped in a tidal embrace that renders one side a blistering desert and the other an icy wasteland. So, how can we know if a planet can truly sustain life? How can we recognize a world where biology might flourish for billions of years, as it has on Earth? Finding a planet in the habitable zone is only the beginning, a first step in a far longer journey to trace the fingerprints of life beyond our world. A journey that may ultimately redefine our place in the vast, silent expanse of the universe. The foundation for Kepler-452b's Earth-like potential lies in its parent star, Kepler-452. Remarkably, this star is almost a mirror image of our Sun. Kepler-452 is a G2-type yellow dwarf, just 11% larger in diameter than our Sun. Sharing the same spectral class, it offers something crucial: stability. Unlike volatile red dwarfs that unleash violent flares and emit intense radiation, Kepler-452 maintains a calm demeanor. This means hypothetical plant life on Kepler-452b could rely on photosynthesis similar to Earth's greenery without facing deadly bursts of X-ray energy. Most importantly, this star boasts an astonishing lifespan stretching billions of years. In fact, Kepler-452 is estimated to be about 6 billion years old, nearly 1.5 billion years older than our Sun. That matters. The evolution of life, if it occurs, requires immense stretches of time, millions, even billions of years, for single-celled organisms to evolve into complex, intelligent life. A long-lived, stable star like Kepler-452 creates the stage for such a transformation. It is the bedrock of sustained habitability, the minimum requirement for a planet to preserve a life-friendly environment over geological timescales. The orbital characteristics of Kepler-452b add another promising layer. Its year lasts about 385 days, nearly matching Earth's. Its distance from Kepler 4.522 is strikingly similar to the Earth-Sun separation, placing it in the sweet spot, not too close to scorch the surface, not too far to plunge it into a frozen wasteland. One more critical advantage: Kepler-452b is not tidally locked. This is monumental. Tidal locking, where one side of a planet eternally faces its star, while the other side remains in darkness, creates a world of extremes. This phenomenon plagues many planets orbiting red dwarfs, like those in the GJ12 system, rendering them inhospitable. Such extremes create catastrophic temperature gradients, making life nearly impossible. Kepler-452b escapes this fate, allowing heat to be distributed more evenly across its surface. No devastating temperature gradients. Instead, what emerges is a stable, temperate world, a vast and balanced environment capable of nurturing complex ecosystems over time. This is not just an advantage, it's a profound opening in the search for a truly Earth-like world. After understanding its parent star, the planet's physical characteristics and internal structure reveal the true extent of its potential. Kepler-452b is about 1.5 times the diameter of Earth, placing it in the category of super-Earth planets, larger than Earth, yet smaller than the gas giants like Neptune. However, its surface gravity is estimated to be 2.2 times stronger than Earth's. Imagine moving across a world where everything weighs twice as much. This gravity would profoundly influence geology, atmospheric dynamics, and even the trajectory of biological evolution. Yet this immense gravity comes with a significant advantage: the ability to retain a dense, protective atmosphere. Such an atmosphere would moderate temperature swings between day and night, shield the surface from intense ultraviolet and X-ray radiation from its star, and block high-energy particles and micrometeoroids. This protective blanket is critical for the survival and stability of complex molecules, the building blocks of life. It is an advantage smaller planets like Mars lack, where a thin atmosphere cannot withstand the relentless pull of space. Kepler-452b's average surface temperature is estimated at 80 degrees Fahrenheit, a range ideal for liquid water to exist on the surface. However, scientists express concern. The planet likely receives about 10% more stellar energy than Earth, creating a serious risk: the onset of a runaway greenhouse effect. This creates a serious risk: the onset of a runaway greenhouse effect. If carbon dioxide levels accumulate too much, the excess heat could be trapped, evaporating oceans entirely and transforming the planet into a scorching wasteland, much like Venus, where surface temperatures are hot enough to melt lead. Climate simulations suggest that if Kepler-452b's atmospheric CO2 concentration equals or exceeds Earth's, it could enter a state of extreme thermal imbalance within a few 100 million years. Some researchers compare its potential conditions to Earth's Mesozoic era, the age of the dinosaurs, when global temperatures were higher and atmospheric CO2 levels far exceeded today's concentrations. With its similar parameters, Kepler-452b might represent a cosmic version of Earth's deep past, a primordial stage where ecosystems, if present, could have developed under conditions long vanished from our world. Kepler-452b is more than just a planet in a prime location orbiting a stable star. It possesses physical characteristics that ignite profound questions. But to fully grasp its potential, we must look closer toward its surface, where terrain, water, and perhaps even the earliest ecosystems may hold the next chapter of this extraordinary story. From estimates of temperature and atmospheric conditions, one fact stands out. Kepler-452b's gravity is 2.2 times stronger than Earth's. Such immense gravitational pull would make the formation of towering mountain ranges or vast chasms like the Grand Canyon highly unlikely. Under this crushing force, tectonic activity would be compressed, limiting the planet's ability to push material upward or allow for deep subsidence. The result, a largely flat and uniform landscape, starkly different from Earth's rugged mountain chains and complex valleys. This difference would not only reshape the planet's appearance, but profoundly influence the distribution of ecosystems and local climate patterns. Planetary science models suggest that Kepler-452b may host sprawling, shallow oceans. With water spread broadly across its surface rather than segmented by massive continents. This scenario resembles Earth's ancient Mesozoic era, a time when life first transitioned from sea to land. A process that occurred hundreds of millions of years ago here, but on Kepler-452b, it could unfold on an even grander scale. Such global oceans would stabilize the planet's climate thanks to water's natural ability to regulate temperature. The role of water, if abundant, cannot be overstated. Water is not only the medium for all biochemical reactions essential to life, it also acts as a powerful climate buffer. Helping the planet avoid a runaway greenhouse effect. Water's unique ability to absorb and slowly release heat reduces temperature swings between day and night and across seasons. Fostering an environment that is stable, temperate, and conducive to life. If Kepler-452b possesses vast liquid water reserves and an active hydrological cycle, it could sidestep the fate of Venus, where CO2 trapped heat and choked off any chance for life. Shallow oceans would also allow sunlight to penetrate deep into the water column, creating ideal conditions for photosynthetic life such as plankton and algae, the foundation of any marine food web. Their presence would spark nutrient cycling and fuel the growth of complex ecosystems. But this raises an astonishing question. What if these conditions have existed for billions of years? Could Kepler-452b harbor an entire biosphere, an evolutionary trajectory completely distinct from Earth's? Could it sustain life forms so alien that they defy every frame of reference we know? Assuming vast, shallow oceans warm to an average of 80 degrees Fahrenheit, with a flat terrain and abundant sunlight from a stable star, The first life on Kepler-452b would almost certainly begin in the water, much like it did on Earth. We might imagine a thriving aquatic world, starting with microscopic single-celled organisms, then evolving into more complex multicellular life, similar to how cyanobacteria once dominated Earth's early seas. In regions with consistent light, thanks to Kepler-452's spectrum being strikingly similar to our Sun's, plant-like organisms could harness photosynthesis to convert light into chemical energy, just as plants do here on Earth. This suggests that if there are leaves, they might appear green or even blue. Depending on which wavelengths of light they absorb most efficiently. Picture alien shores lined with strange, thick-stemmed plants, broadleaves sprawling to capture every photon. Adaptations driven by the planet's crushing gravity. But what about land animals on a world with gravity 2.2 times stronger than Earth's? Terrestrial creatures would likely evolve into short, stocky forms, optimized for weight distribution. Expect thick, dense skeletons for structural integrity, or even hollow yet reinforced bones to reduce weight without sacrificing strength. Muscular legs would be essential, possibly with wide splayed feet or even multiple limbs to maximize stability. A powerful heart and circulatory system would be vital to pump blood against relentless gravitational pull. And then comes the most contentious question, could anything fly here? Many exobiologists argue that flight would be virtually impossible under such gravity. Rendering wings useless. Yet others propose a fascinating counterpoint. If Kepler-452b's atmosphere is significantly denser than Earth's, aerodynamic lift could increase dramatically, compensating for gravity's strength. In that scenario, flying organisms might evolve massive wingspans, lightweight skeletons, and behavior akin to prehistoric gliders, soaring on thermal currents like ancient parasaurs. Still, the challenge is monumental. Flight under these conditions would demand biological innovations far beyond Earth's examples. A fusion of strength and extreme lightness that defies our imagination. Yet, if the atmosphere is dense enough, it becomes possible. Some forms of life with wings and body structures adapted to a dense atmosphere might still master the art of flight? No matter how alien these life forms appear, scientists believe they would still adhere to universal biological principles. The ability to extract energy from the environment, rely on genetic systems for replication, and evolve through natural selection, adapting continuously to a changing world. Kepler-452b is not just a potentially habitable planet, it could be a cosmic laboratory. Where the familiar rules of biology are tested against an environment unlike any we know. But even if life emerges, it faces an eternal truth. The same forces that create it can one day destroy it. While Kepler-452b offers the tantalizing prospect of a habitable world, science is not just about marveling at wonders. It is about confronting harsh realities. Assessing the risks is just as critical as dreaming of possibilities. The first and greatest concern is the runaway greenhouse effect. If this occurs, surface temperatures could skyrocket beyond control, plunging the planet into a fate eerily similar to Venus. A world once thought to harbor oceans, now a scorching inferno with average surface temperatures near 470 degrees Celsius and atmospheric pressure 92 times that of Earth. According to models from NASA Ames, if CO2 concentration crosses a critical threshold, entire oceans could evaporate in mere millions of years, a blink in cosmic time. Another formidable risk lies deep within the planet: intense tectonic and volcanic activity. If Kepler-452b's core contains significantly higher concentrations of radioactive elements, uranium, thorium, potassium-40, and Earth's, their decay could generate colossal heat, driving relentless tectonic shifts and catastrophic volcanic eruptions. While geological activity is essential for recycling carbon and sustaining life's chemistry, excess could spell doom. A planet ravaged by mega eruptions and violent quakes would struggle to maintain ecological stability. Finally, there is the silent but terrifying danger of biological and immunological threats. If Kepler-452b harbors life, whether microbial or more complex, our immune systems would be utterly unprepared for alien pathogens, viruses, or bacteria with biochemistry completely foreign to Earth. Even accidental exposure could unleash pandemics beyond the grasp of terrestrial medicine. Or trigger severe allergic reactions to unknown compounds. This is an invisible yet profound barrier, a sobering reminder that the universe hides not only beauty but perils beyond comprehension. Conversely, we could become the invaders, a biological threat to any native biosphere. Echoing the tragic history of European microbes decimating indigenous ecosystems, upon contact with the Americas centuries ago. In the grand view, Kepler-452b underscores a fundamental truth of planetary science. The closer a world resembles Earth, the more dangerous it becomes if misunderstood. Life may exist, but stable, advanced, communicative life is another question entirely. And so, standing on the edge between hope and hazard, one question looms larger than all. Is Kepler-452b truly our best candidate among the stars, or simply a beautiful illusion? The quest to find planets like Kepler-452b worlds that may cradle life is one of humanity's most inspiring scientific odysseys. It is a story of ambition and mystery, a testament to our relentless drive to explore. Yet for all the billions of potential worlds scattered across the cosmos, and for all the promise that Kepler-4042b seems to hold, we are confronted with an undeniable truth. Earth remains the only world we can call home. Every discovery of a distant exoplanet, Every fragment of data decoded by our great observatories is more than a step toward understanding the universe. It is a profound reminder of the fragility and value of our own planet. The story of Kepler-452b is not just about the search for life beyond Earth. It is also a warning, a call to look inward. Earth, with its delicate climate, its oceans of liquid water, and its life-sustaining atmosphere, is a singular oasis in an otherwise cold and endless void, a miracle suspended in space. We live on a rare world. The search for a second Earth does not diminish the importance of the first. On the contrary, it amplifies it. Are we truly cherishing and protecting the only home we have? This question, simple yet profound, may hold the key to humanity's future, not among the stars, but here, on the planet that gave us life. And sometimes the greatest wonder in the universe is not the world we seek, but the one we already have. And sometimes the greatest wonder in the universe is not the world we seek, but the one we already have.